What's up, everybody? Welcome to another episode of Archill Podcast. Today I'm joined with Franck Pachot. Franck has been in database industry for about 30 years now. He has worked at places like IBM, Air France, and CERN. Currently, Franck is a developer advocate at Yugabyte, the company behind YugabyteDB, the open source distributed SQL database for mission critical applications. I'm super excited to share this episode with you. We have talked a lot about databases and beyond. So without further ado, here it is. My conversation with Franck Pachot. Enjoy. So you've been in this database industry and around databases for more than 20 years, right? I'm correct.
Yeah. I don't even count, but that's nearly 25. Yeah.
Yeah. So you're the best person to ask this question now. So what were databases back then, and how did they evolve till now? Can you share that with us?
Yeah, basically, I've seen the evolution. I've always been working with SQL databases, DB2 at the beginning, Oracle a lot, and then more open source like Postgres and now Yugabyte. So the evolution I've seen when I started was all client server, so the application on the client and the database on the server, and then with an application server in the middle. And then I've seen the trend of NoSql, even if I was not completely convinced by it, but was interesting to see that to scale. And then the new trend, distributed SQL. Basically, I've been working with traditional databases until 2 years ago, where I joined Yugabyte, and then I learned about distributed systems.
Yeah, we'll talk a lot about that. And one kind of fun follow-up question. So back like 20 years ago or 15 years ago, how was it? I mean, did companies acquire some servers? Were there some service providers? Obviously, there was no cloud, right, back then. So how was it kind of administrated, this database stuff? So let's say I wanted to use a database. How could I do that as a company?
I think there are two cases. I can just explain you quickly one of my first job where I was working as a consultant for a small team within a big company. So this big company was full IBM, so they had DB2 databases on mainframes. And I was working in the small team of in accounting, where they wanted to build their own application because it was very slow to build the specifications, ask for the IT to develop something. So they wanted to build something by themselves. And I started this with Borland Paradox kind of access, so something with no server. Okay. And they wanted to build something on a server. And then I had to install. We had Oracle that was giving us a trial with the Oracle database. We had Sun giving us a server. Of course, they were all interested because as the company was fully IBM, all the others were interested to come by one door or one window into this. And then it was a great experience for me because I had to install all that without knowing anything. But I compare that today to the DevOps approach, where you have an application to develop and you have to build the infrastructure to develop it. The difference is that at that time it was not a click on a console; it was really unboxing the server, unplugging, and asking to the senior people what means an IP address, a subnet, and to configure all that.
So basically, it was some kind of a custom hardware machines, right? Servers, and you operated on them directly, right?
Yeah. So always physical servers, physical disk directly attached to the server. So not easy to install because to install it you need to know everything about storage, mirroring, network, and all that. Not just the usage of it, and also not easy to plan. For example, if you have a new application, you don't know really how many CPU, how many disks you will need. And when you buy it, it's an investment for the next years. So that was also something quite difficult. But the advantage was that all was physical, all was there. So maybe it was easier to learn exactly. When you plug the cables, you learn about the network probably better than when provisioning a VPC somewhere.
Yeah, I imagine like how hard it would have been to scale vertically these systems, right? You would have like bought some machinery, plug it, and things like that, probably, right?
Yeah, there were no vertical, except in the big mainframes, the big servers. But yeah, everything was over provisioned. But also maybe we were also doing more tuning and design rather than starting and thinking that we can scale later. So yeah, maybe that compensated. But the release cycles were completely different. At that time, you were writing the specification to build an application in the next 2 or 3 years. That's completely different. Today, we need to go faster.
Yeah, definitely. Okay, now speaking of databases, let's dive a little bit deeper. And I'm super curious. Like the first thing which comes to my mind is how this data is actually stored on disk. I mean, is there some how do we like store this much of the data and then query them efficiently? And but in particular, let's talk about how this data is stored, and maybe we can talk about Postgres because let's say.
So yeah, basically, what I like to explain to people is that finally your database doesn't work on disk. It stores on disk because there are volumes that cannot fit in memory, but everything that you do works in memory. For example, in Postgres, in the shared buffers, when you connect, when you insert rows, your session will just write to a buffer in memory. And then the database in the background will write this to disk. But the first interaction is with memory, and memory is limited, and this is why it goes to disk in two ways. First, the state of the data is written, but also the write-l logging, the redo logs, to protect the memory, because you work in memory, and you don't want to wait for the disk write. That would not be scalable at all if each insert had to wait for the disk, especially at that time where the disk latency was in 10 milliseconds, for example. So you work in memory, and the memory is protected with the write-l log that is fast to write, but not easy to read. So on one side, there is this log that is written, and on the other side, the blocks are written to disks in a way that is easy to read when it is not found in memory. So this way is with a lot of indexes, because without indexes, you just have to read the whole table to get maybe the few rows that you need. And with indexes, it looks at your predicates to read only the necessary blocks from the disk. So yeah, maybe I should have started with that. It is stored on disk, on a permanent storage, but a block device. For example, you cannot store in S3 in the cloud, except if it's read-only for data warehousing, but an active database where you update a lot, you update per blocks. Blocks can be 8K, usually 8 kilobytes, but that's also a specificity. The storage must have low latency and be a block device.
Yeah. Okay. So I have lots of follow-up questions now. So basically, when we write, the first thing which we interact during write is memory, right? This in memory, and then we kind of fill some buffers or blocks in memory, and then this is synchronized with the disk, right? Because disk is more like heavy operation to write on. Is that correct?
Yeah.
And what about
and this technically is called a checkpoint, where it's synchronized to disk.
Yeah, and you mentioned something about this write logs, if I heard correctly.
Write logs, WAL in Postgres, or some databases call that journal or transaction logs or redo logs.
Okay, so maybe we talk a bit when we get to the transactions about that. So now the next question is about querying data, about reading data, okay? Can you walk me through the process? So let's say I open some IDE, I don't know, or some terminal, and I write a simple select script.
Yeah.
Select all from users table, for example.
Yeah.
Can you walk me through what happens when I hit enter all the way around from disk to my UI?
Yeah. So when you hit enter, you send text to the database.
Yeah.
It's a
Good.
language, SQL, and it's text. So you are connected. Probably you are already connected, means that you have a connection to a process that will first parse your text to understand its syntax, what is select, what is the name of the table. So the syntax, the semantic, if it finds something that should be a name for a table, then it looks into the dictionary that is also called the catalog, which has more information about it. So I select from users. User is a table. It's a logical object, but physically, what is stored there is stored in files, and it has colons and specific data types. So all that is in the dictionary or catalog. That is the metadata about your data, and then this SQL text becomes code. First there is an optimizer that builds the procedural code to access to the data, because SQL is declarative. When you say select from user, you do not tell the database how to read user. Do you read from the beginning to the end, from the end to the beginning, or going through an index or whatever? So there is an optimizer, also called query planner, that determines from its information that is in the catalog and from your query the best access path to the data. So for example, if you do a select star from users, you want to read all rows, then probably a full table scan will be used because it's faster to read all rows. And then it reads an execution plan. So for the moment, nothing is executed for your query. It has only compiled your SQL code, compiled to the internal operations that will happen to access data.
Okay.
Full scan, if you added an order by, there is a sort operation. If you have some conditions, there is a filter. And then this execution plan is executed, and this is where it will actually access to the data, depending on the operation. If it's a full scan, it will go to the first block where the rows of the table is stored, so in a specific file, specific offset, and read from there. If you have an index, for example, if you do a select star from user where name equals something, and you have an index on name, you have another access to your data. Rather than reading all and discarding many of them and keeping only one row, you have an index who knows exactly in which block it can find this name and in which block it cannot find this name. And then going through the index, it reads the blocks. So if you want to read one row from a big table, going through an index will be faster because you will read a few blocks, 2, 3, 4 blocks, and get your row. If you want all rows, it's faster to scan everything. Basically, like in a book, if you have a book and you are searching for one specific word that is in 1 or 2 pages, you go to the index. But if you want to find a word that is very common in all pages, you just start from the beginning and looking to the end. And the index will tell you which page to go. So finally, you have to read only one or a few pages. The goal is to minimize the number of pages that you read. And it's also called pages. Those buffers, when they are written to the file as block, they're also called pages because that's the unit. From memory, you can read just a few bytes. But from the disk, reading a few bytes takes the same time as reading a full block. And then it's better to optimize the reading of the blocks.
Yeah. So it's like the minimum unit which we can read from the disk is like a block or some chunk, right?
Yeah.
Okay, uh, got it. So now let me touch kind of hot topic about this relational databases, which is called this ACID properties. And can we talk a bit about each of them in Postgres, for example, and yeah, then move on.
Yeah, so the idea of ACID properties is that in a database, you have multiple users reading and writing on the same data. If you don't, there are databases that you can embed in your application where you are the only one. For example, if you use SQLite for a local repository, you don't really care about other users because the database is all yours. But for most OLTP applications, you have many users. For example, in a bank, even your own account, it can be accessed because someone is transferring money to it, because you are using the card to debit, and maybe your wife is
Yeah,
withdrawing money elsewhere. So there are some concurrent access, and the you have to manage that. And also, you have access that are more than just one read or one write. The typical example is that in a bank transfer, you withdraw from one account and you do a deposit on the other account. And those two operations must be atomic. You cannot stop in the middle. Even if the data center burns in the middle, you need to be sure that you still have a state either before or either later. You still have the state if it burns, because usually it is replicated on another one. But you need this guarantee. You cannot have money withdraw from an account and not added to another one. So that's the atomicity of ACID. And you don't need it in the database. But if you don't have it in the database, then you have to manage it in your application. Like locking something and having a background process that will do the cleanup. There is a lot to do. The idea of the ACID properties is that you can really develop your application as if you are alone on your database. And it will still work with concurrency. Maybe it will take more time because it has to check for conflicts and maybe lock some information, but it still works. So you don't have to code for it. You code only your business logic. You don't have to code for the fact that maybe someone is writing while you are reading, and more important than code, you don't really have to test it, because that's not easy. How do you test that 1,000 concurrent users
yeah.
maybe access the same data and you are sure that at the end it works? That's not easy to test. So it's easier that the database vendor has tested all those single combination of reads and writes, and then you can rely on it for your business logic. So that's the idea of ACID. So
By the way,
atomicity.
I loved your definition about it, as it's like a like amazing like example that like you code as if you are the only user, and this concurrency stuff is kind of managed by the database itself. I just loved it. I wanted to admit it. Yeah.
Yeah, and people forget about it. Maybe we'll talk a bit about NoSQL database later, but when you start an application and you don't think about how it will run in production with all this concurrency, then you may think that a database is easy. You just read and write some data. But when you have to think about what can happen in the middle, that's more complex. And when you have atomicity, so basically the database goes from one state to another with multiple reads and writes in the middle. The C is about consistency. It's more that you can also add some integrity constraints to be sure that the data is valid. For example, if you withdraw money from an account, this account belongs to a customer. If you do this operation without being sure about which customer it is, then you have broken something. So this is where you have referential integrity, that your whole database is consistent. And when you go from one state to another, the database will ensure that this state is still okay. And also we mentioned that you have indexes, and indexes are redundant storage, storing the same data but in a different physical organization for a different access. And the database must ensure that this is all consistent. If you have redundant storage, but it has missed some changes, then you have inconsistency. So that's the C. And then maybe the most complex is the isolation. The idea here is that you work on the database without seeing what the others are doing. And then the database will guarantee that if you commit, so if you end your atomic transaction, it can be successful only if there is no conflict. But for isolation, there are multiple levels where in some level you may have to care about the concurrent access, because the best isolation that is serializable, not a lot of database implement it, and sometimes there are some performance issue with that. So sometimes you have to release a few of it and use lower isolation level. And the last one is easy. Durability is just that your data must go to persistent storage, at least at commit. If you didn't end your transaction, it's not important because you cannot stop because of this atomicity. You just have to go back to the previous state. So the intermediate state can be lost. So this is also why you can work in memory. It's fast. But at commit, this redo log, this write logging, must go to a persistent storage. And today it's more than disks. Usually it must also go to another standby database, another replica, maybe another data center, because you want it to be durable even if a disk burns in a data center, for example.
Yeah, and just one question about isolation. So, just to say this example about withdrawing money from account. Let's say I'm withdrawing money, and concurrently at the same time, my wife is putting money in that account. So basically, like by default, if we change this amount at the same time, either of us will fail, right? Because of the isolation.
Yeah, then you have two implementation of it. It must fail because it conflicts. The problem is more that when you withdraw, you also look at the total amount. And if it is changing, then maybe your decision to withdraw will change. For example, if you are both withdrawing money and you are not aware of what the other is doing, the risk is that you withdraw more money than what you have. So that, you need to have this consistent view. And if there is a conflict, for example, if the database detects that you have read a state and taken a decision on it because you have written something after, but this state is not valid anymore, then it has to tell you you need to redo it, reread the new state before doing it. And there are two ways to manage that: the optimistic and pessimistic way. The pessimistic is when you lock what you access. So depending on the database, it may lock when it reads or only when it writes, and then detects the conflicts. The idea is that you read the total balance of the account, then nobody can change it until you are done with your transaction, because you will take decision on it. And the other way is the optimistic way, where you don't log, so you have better concurrency, but then you may have an error that is not a real error. It's just that you have to retry it, because there is a way where the operation were ordered that cannot be completed. So you get an error and you have to retry it. And
so it's all about trade-offs.
Your application
right?
must do it. Yeah.
Yeah. So it's about like the concrete situation. You prefer either pessimistic situation or optimistic one, right?
Yeah. Maybe we can take another easy example. You want to book a flight for a trip. So you ask if this flight is free, and then you think about it and you will pay about it. And you don't want that 5 minutes later, time to pay, you don't want that the website tells you, oh, this flight is not there anymore. So it will try to lock it, but it will not lock it for days, because that will block others. So maybe it will lock it for 5 minutes. And if you complete your transaction, if you pay and book it, then you have it. After a while, it will go to this optimistic way where maybe it will tell you, oh, sorry, it is not available anymore.
Yeah, that's a great example, actually. Thanks for that. And now, like, to complete our kind of journey about relational databases, let's talk a bit about transactions. And you mentioned this atomicity, you mentioned this logging mechanism. Can you tell us, like, let's say I have a transaction. First, tell us what transaction is, maybe, and let's say I have two independent writes in this transaction, and let's say second write fails. And so let's describe that bad scenario first, and then let's describe a commit good scenario when both writes are successful, and how is that committed in the database.
Yeah. So if I take the example of Postgres, if I start a transaction, begin transaction, I write, let's say, insert, and I have another write, maybe an update on something else or the same, and the second one fails, the transaction is cancelled, because the database, you cannot go further because you had an error, and then you have to roll back, go back to the previous state. So everything that you have done is undone. And anyway, it was not visible to the others because of the isolation.
Yeah.
So it's undone, and you have to redo it. There is a possibility, if you have a long transaction, there is a possibility where you don't want to redo everything. And then you can take save points during your transaction, so that if one fails, you can just roll back to the save point and redo it, maybe differently. In practice, this is not used a lot in Postgres because save points are not very optimized. And also because usually, especially for OLTP application, you have short transaction and then you just redo it. But for example, in Oracle takes a save point at the beginning of each statement. Then if it fails, you can continue the transaction. This is made also when a user is entering statements, doesn't want to redo. When it's the application, usually the application will roll back everything. And in Yugabyte, we also take a save point at the beginning of each. One advantage of this save point is that we mentioned that in case of some conflicts, the database may have to say, oh, we have a conflict, we have to cancel it, and you retry it. If you have the serializable isolation level, where the whole transaction is covered by the isolation, then there is no other solution than getting an error, and the application must redo it, because the database doesn't know everything that you have done during that time. But when you have the lower isolation level, that is called read committed, where it does the same as serializable, but for each statement in a transaction. And then some databases like Oracle or Yugabyte, they can roll back the statement to this save point and retry it themselves. The point is that if you run something and you didn't get any result yet, then the database can cancel it and retry it to solve this conflict. But as soon as it has already sent a part of the result, it cannot retry it because it doesn't know what you have done with this result. Maybe you have sent an email, maybe you have written to a file, and then your application must handle that.
Okay, and basically, like, about this logs. So these kind of mutation statements are single record in this log structure, whatever. Can we say like that? And these elements of this log are kind of re-executed if we need them, right? That's how we construct this database state. Is that correct in that transaction?
Yeah, basically there are two things. When the database retries the statements, it retries the whole statement, maybe an update that touch multiple rows. The write-rl log is more for recovery. If the instance crashes, everything you have done in memory is lost, and then it will use those logs, but they are really low level. Huh? They write everything that is physically written to a block just to redo it, but for recovery purpose. Yeah.
So just to clarify it once again, so if something bad happens and things crash, we re-execute these logs to construct this memory again, right? Which we had before this crashing happened. Amazing, great. Now I got it. So
actually, there is even another step, because when it crashes and it starts again, it will apply all the redo logs to rebuild the same state. But at this point, there were some ongoing transactions, and those must be rolled back because they were disconnected. The application just had an error. And then, so it rebuilds everything, even the uncommitted changes. And then it will roll back those that were not committed. And then you have a clean state with only committed changes in the database.
So just to clarify again, so first this log execution will include these uncommitted changes as well, and the second step will clean them out, right?
Yeah.
Amazing.
You have a kind of roll forward and then roll back of what was not finished. Yeah.
That's super interesting. So now let's move on to NoSQL world. So can you tell us, like, what's the difference between traditional relational databases and what was the need to create such concept of NoSQL databases at all?
Yeah, mainly the need. I mentioned that everything is done in memory. And the problem is that the memory is more difficult to scale, especially it cannot scale out. For disks, you can add more disks. And with a SAN or a NAS, you can have really a lot of disks when you need to. But this memory is shared. The idea of all session writing to memory before disk is also to detect those conflicts. If they were all writing to the same file from different processes or different servers, then everything would be corrupted. You need a single point of truth for those blocks, and that's the memory, and it is shared memory because all sessions access the same one, of course, protected with some latches, internal locks. But
this is for relational databases, right?
Yeah. This is relational databases. And then you can have a lot of features with that. But the problem is that you have this monolithic memory that you can scale up. For example, you can stop your server and start a larger instance in the cloud. But first, this is downtime. And you cannot scale out. So if you need more memory than what you can have on one VM, then you have no possibility because you cannot share the memory between multiple VMs, between multiple hosts. So the idea of NoSQL was to find a solution for that, being able to distribute the database, not having this single read-write instance with its own shared memory, but being able to scale horizontally the database on multiple nodes that may be on multiple racks, data centers, even availability zones, or maybe regions. So having this full scalability, but then all those ACID properties that we have seen are not easy to scale out, and especially at that time. So we are talking after the years 2000, was not easy to scale out, especially with the need of those big companies that had to scale out to multiple regions, and there is a latency. So the idea of NoSQL was like, let's remove all the features that make it difficult. If you have a complex transaction with multiple reads and writes, and you need to ensure isolation, atomicity, that means that all sessions must have an idea of the transaction status of the logs, and those were in memory. If you want to replicate all this information logs to multiple regions, then that means that each write will take tens of milliseconds or hundreds of milliseconds. So the idea of NoSQL databases was remove everything that is not scalable in the SQL databases and go really to the basic. Just read and write single objects. Do not join two tables, because if you join two tables, you have to check the consistency between them. So the idea was, rather than building relational databases where your transaction will touch multiple tables, think about a single use case and model the structure for this single use case as one document, not multiple tables. So the big advantage was that reading and writing one document can send the operation to only one shard, one partition of the database, just taking the primary key, the key of the document, and then everything is local there, and another transaction working on another document will work on another server without the need to share anything with the other. So makes it easier to distribute. And also was a time where people find that SQL was too complex, relational databases were too complex, especially because the release cycles were faster and faster, and then some of them find it easier to use documents on NoSQL databases. Until some point where at some point they realized that they have to add more code to manage the consistency of it. Everything that the database doesn't do, the joins, the consistency, they had to do that in the code. So basically, NoSQL databases were really good for single use case, but a complex application has multiple use cases. For example, if you have an e-commerce application, I am a customer, I order, that's the view. The view on the database is a customer has orders and orders products. But then when this is done, the stock management has to access with another access pattern. They don't really care about the customer. They care about the products, which orders. And that's another use case. So with NoSQL databases, they are optimized for one use case, one hierarchy, and then they have to replicate data to another service. So you have microservices dedicated, but a lot of data propagation from one to the other.
Yep. So basically, as I understood, with NoSQL databases, a lot of things should be done on application level, right? To kind of manage all these processes. But one thing I want to kind of dive a little bit deeper is this concept of documents. So can we talk a bit more, maybe with some examples of these orders and customers, which you said, how this kind of structure will be stored in NoSQL database, and how is it different actually? I mean, how is it different from this relational one with lots of tables, right?
Yeah, the idea of relational one is that you store the customer information in one place, the order information in another place, the product information in another, and then you join that at runtime.
Yeah.
Depending on your use case, you will join customers to orders or products to orders. So you have this agility to join that at runtime. The idea of NoSQL databases is that we focus on one use case, and then rather than joining at runtime, looking at one customer and all his orders, then let's store them together. Because that's also a performance problem. Typically, I'm a customer and I order something every month, which means that physically my orders will be scattered within the database. But if I want to query my last orders for the past 5 years, then physically it will be multiple random IO in those scattered places. If everything was stored together at the same time in a single document, then reading it is faster. But of course, that also means that you have to rewrite the document each time. I mean,
Yeah.
I do a new order, and if I want to update a document with all the customer orders, then the document must be updated. So there are trade-offs everywhere. But also, I think NoSQL also was very popular because applications are written in object-oriented languages, Java for many of one, but others. And there you have this view of a hierarchical structure. You have a class of orders, and you have a class of customers, and you have this many to one relationship on it that exists in the object, and mapping that to the relational database required ORMs like Hibernate, for example. So NoSQL databases were also very popular because they provided this API directly. And now with JSON, for example, where you just ask for one customer and all of its orders, and they all come together without a join, without getting a tabular result like in SQL. So makes it easier. But today, SQL databases have evolved to store also some JSON objects. So today you can also store documents in SQL databases.
Yeah, then that's a good point you touched. So then, what is the decision-making process in now? Let's say that if I can store the same data structures in Postgres, let's say, or some other relational databases, and in NoSQL databases as well. So, what's the factor which we should pay attention to decide which way to go?
I don't think it's about data structure now because you can do a lot in both, but about transactions and this ACID properties. That's the big difference between them. For example, if I take a NoSQL database like DynamoDB, the typical use case for DynamoDB, and this is also why Amazon started it at the beginning. Of course, now it has a lot of more use cases. Was for the e-commerce application to put orders in the cart. So you browse the products and you say, yeah, I want to buy that, I want to buy that, I want to buy that. This needs to be stored. It also needs to be persisted because if I'm disconnected and I connect again a few days later, I want to see and continue my order. And not only me, but the vendor also wants me to continue because they want to sell it. So this is very good in a NoSQL database because you don't need those ACID properties. You need the durability, but nobody will update my own cart until I pay and it becomes an order where many use cases will use it. So that's a good one for that is probably easier to build on a NoSQL database because you don't need additional code, even if there is no ACID properties, and you have this easy API. But if you need more complex transactions, storing something where the application will evolve with new access patterns, then probably the agility of relational databases will be useful. NoSQL databases, you really need. People think that NoSQL databases are more agile about the structure. It's true about the attributes of the documents because there is no strong schema on it. But the key is very important. You need to know your access pattern in advance. You cannot just come like with a relational database where marketing has a new idea, like now we want to see to analyze the sales per country or per whatever, and you don't have to change the application. Maybe you will just add an index to get fast access to this access pattern without changing the application. With NoSQL, you will basically need to build a new data store for this specific need.
Yeah. Thank you. It was super insightful and super interesting. And now let's move on to like the next big thing, I guess. We talked about relational databases, NoSQL databases, and now we have some crazy technologies around like Google Spanner and Yugabyte as well, right? And let's talk about these distributed databases. maybe with Yugabyte context, and let's talk about Yugabyte as well. But first, let's talk. I mean, uh, again, can you enlighten me the decision process when we should choose to choose distributed databases over maybe some simple monolithic ones or NoSQL ones?
Yeah, first it started with Spanner, and the reason Google decided to build a new database was because of all this additional code they have to put on NoSQL. I mean, Google had to scale to multiple regions, and they have the infrastructure for that. And they had big tables, for example, as a NoSQL database, but they realized that the lack of SQL features made the applications very complex. And this is where they started to build something with the same distributed storage as NoSQL databases, but adding on top of it what comes from SQL. So having those ACID properties, having this catalog or dictionary, the optimizer, so that you can write SQL queries without really knowing how it is stored, and adding all that. And they did that with Spanner, and it was quite successful, at least for them. The problem is that it's really tied to their cloud, so it's not a general solution for everybody. But then came Cockroach, building Cockroach DB. And I think it was built by people that have been working on Spanner before. And their idea was to do the same thing, but that can work in any cloud or even on premises. And a few years later, YugabyteDB came with the same architecture, but the idea was that Spanner had really limited SQL features. Cockroach added more, and for example, started to use the Postgres protocol to talk to the database and a few Postgres features. And given how things were going, people going back to SQL databases, the idea of the Yugabyte founders was that the future is to have all SQL features. All SQL features that Oracle, Postgres, DB to SQL Server has added through years to relational databases. We will need the same on this distributed architecture. So the idea of Yugabyte was, rather than rebuilding all those features one by one, let's try to take Postgres, which has a lot of features, which is open source and very clean code, and plug that on a spanner-like architecture. And
Okay.
that was the idea. Just plug it and then optimize, of course, some things.
Yeah. So before I dive into some questions about the architecture of Yugabyte, can you tell us like what are the use cases of such large distributed databases? I mean, do ordinary small startups use them, or some big things are using them, or when do we use them?
Yeah, that's a good question, and it's good to start with it because people immediately think about the need to scale out, like Amazon, Google, Microsoft are big companies that need to scale out to multi-region and all that. And of course, it's a case. But being distributed has many other advantages. First is high availability. The problem with monolithic databases, with their single memory on a single server, is that if it crashes, we have seen that it can recover with the write-ahead logs, and even it can even fail over to a standby database that receives those logs and apply it, but it's still a downtime. And today, a downtime is quite difficult. Even if it's fast, a few minutes, usually you need manual intervention, so you need to call someone during the night. A small company doesn't have a big team of DBAs to do on-call rotations. And today we use more and more managed services in the cloud. And then you don't have those DBAs in-house. So the system must be resilient. If you are a customer of a managed service, you have a database service, you don't want your cloud provider to call you at 3 a.m. telling you,
for
oh,
sure.
we had to restart the database.
Yeah.
Can you check the application? Does
Yeah.
it still work? Is the performance still okay? So you need more than high availability where you have fast failover. You really need to be resilient.
Yeah.
So the goal with this distributed system, because everything is replicated, if something fails during the night, you don't have anything to do. Of course, in the morning, you will try to understand what happened. If it was just a network failure for a few minutes, or if a data center has burned, of course, you have to take some decisions to reinstate the right replication factor. But you don't have to manage it immediately, the failover. So that's the main reason. High availability, going further than this simple standby database where you can switch over and fail over. And that's not only for failures. A big problem in monolithic database is that at some point you need to update the system or scale up, add more memory, or upgrade the database itself. And for all those, you have to stop the application. If it's not a failure, it's a planned maintenance, so you know it in advance. That's quite nice. But then you still need to stop the application at some point. You still need people maybe working during the night, on the weekend. And when it is distributed, because you have multiple nodes that are all equal, they can all handle your connections, your process your SQL statements, store their part of data, and then you can just stop one and do whatever you want with it. Restart it with more memory, or upgrade the OS, or even upgrade the database itself, starting a new node, and then you do rolling upgrades, and basically you never stop the application.
Yeah, so basically, to sum this up, the idea of these distributed databases is to have like same kind of sub databases which are equal, which contain same data across different regions, different data centers, and we kind of ensure like 100% availability and no downtime. Even when we need to stop either of those instances, others will serve users, right? That's the idea.
Yeah, logically, you can connect to any endpoint, and logically, you see one database. Physically, there
Yeah.
are multiple ones running behind, but you see only one. And that means I've seen some Yugabyte users with very small database. I mean, 100 of gigabyte. You don't think that you need to scale out
Okay.
because of the storage, for example, there.
Okay.
But they had to be up always because it's an online service, and they didn't want to stop the database. Also, they didn't want to come during the night to stop it when there are less users. So that's a good reason. And of course, databases in terabyte or hundred of terabytes, they benefit from this scalability because you can add more nodes. And also another reason, when you go to the cloud, you need this elasticity. On premises, even if it's easier now with virtualization, like at the beginning where we were unboxing the servers,
Yeah.
on premises, we provision server for the peak of activity. And for example, if you have a peak of activity in summer because it's holidays, or in Christmas because or just before Black Friday, if you have those peaks, you have to provision all the infrastructure for those peaks. If you do the same in the cloud, that will be very expensive. You are cost effective in the cloud only if you can provision for those peaks during 1 or 2 months, and then much lower for the other times. So you need this elasticity, and with a monolithic database, to change that, you can switch over to a standby, but then stop the application. And if you are distributed, you just restart smaller nodes, one after the other, and the application just continues. And when you know that you will have more activity in the next days or month, you add more nodes, and the database automatically rebalance everything.
Yeah, and just one question which just came up to my mind about distributed nature. Can this be the case? I just want to ask you. So let's say on this large scale, like YouTube scale or Amazon scale, when, especially on YouTube scale, okay, when the speed of querying some resources matters, let's say, somewhere. And does it depend on the regions? For example, if application is deployed in US region, for example, and we're accessing some data in Australia, will this distributed nature benefit us that we have these distributed data centers in Australia, for example, as well, and query those? Is that can be that be the case?
Yeah, it can benefit or it can be harmful. So if you are a single region, for example, in AWS, availability zones in one region have 1 millisecond between them. So those calls are not visible by the user. But if you are multi-region, can be hundreds of milliseconds, and then that's a problem. So in that case, you want to do some geo-partitioning. So not distributing, not letting the database distribute blindly across them, but add some information about where are the users. If I am a bank worldwide, but my European customers usually connect from Europe, so it's faster if they have their data in Europe. And even for performance, but even for legal reasons, I have no choice that their data must be physically in Europe also. So that's another reason. So for this, what we do, for example, in Yugabyte, where we use Postgres, we use the Postgres partitioning for that. So the table is partitioned by country. For example, we know the country of the customer, and then we can map the countries to specific places within the cluster. So I can still have a database with nodes in all regions, but say the partition for those and those countries are in this specific region.
Yeah, amazing. So you have a kind of full flexibility and like access to this partitioning stuff. So can we kind of get back to this architecture of Yugabyte? So you mentioned Postgres, you mentioned some spanner-like system. Like, can we go like from top to bottom? Bottom, like what are the kind of components which add up to Yugabyte?
Yeah. So when you connect, you have multiple nodes in your cluster. So maybe, for example, you may have 10 nodes or 10 VMs or 10 containers in 3 availability zones for the replication. So you connect to one, and there you have a Postgres backend. It's a fork of Postgres. There are some changes in the code, but most of the code that runs there is the Postgres code. And it's the Postgres code that reads your query, builds the execution plan. There is some specific code to be aware of the cluster. For example, when it estimates the cost of a join, it will estimate with the latency between the nodes that you don't have in the regular Postgres. So this is Postgres down to the point where at some point you need to read and write some data. And there, instead of reading and writing from shared buffers like Postgres and then local disks, if it's not in the shared buffers, then this is where it sends the reads and writes to the right node. So each node is also aware about where is the data. This means that data must be split. When you have a table, for example, you have your table of users. It has a primary key, let's say a user ID. On the primary key, sharding will happen. Means that it's kind of automatic partition. Like IDs from this number to this number will go to these specific nodes, or in this case, because we want to distribute, it can apply a hash function on the ID and then distribute that. So with this sharding, even a big table will be split in what we call tablets. In Yugabyte, Spanner calls that splits, Cockroach calls that ranges. But basically, those are shards, which are with a size that can be easy to move from one node to the other when it has to rebalance. For example, if you have new nodes, there is some data that has to be copied to the new nodes to balance the load, and you don't want to copy terabytes. So typically, those shards are 10 gigabytes, hundreds of gigabytes. So that's the unit. So when you read and write, depending on the primary key, it will go to a specific shard and send the reads and write to it. For indexes, it's the same on the index key. So means that an index entry on one node may reference a table row on another node. All indexes are global at this level. And then within one shard, this is where we have a code that is completely different from Postgres. Basically, the code was based on RocksDB for the storage. So
Okay.
here I'm going to the storage, and then I will talk about this middle interface that is talking to different nodes. Physically, each tablet is a RocksDB database on the node where it is stored. So it's a LSM tree, different than bit trees, a structure that is more optimized for this kind of access, also more optimized for SSDs, because today for OLTP databases, probably you provision on SSDs. And then in this structure, it can find the key, update the key. And then in the middle, you need to send read and write between the nodes and also know what the others are doing for the ACID properties. So you need to have information about the other transactions and the intents of the other transactions. So this for this intermediate level, the code is based on Apache Kudu and uses the Raft algorithm for replication. So basically, if I take like we did before, if I select from users where ID equals 42, for example, the Postgres layer will build the execution plan going through index, probably for that. And then will determine which replica is the Raft leader. In Raft, there is a leader election where there are one leader and followers, and it will read from the leader. And the writes will also go to the leader. You need that to be consistent. If you read and write from different places, you don't have this consistency. It is still distributed because of the sharding. Of course, if all sessions are updating the same row, they will all go to the same place, but they update different keys, and this is distributed. So the reads are always from the leader, and the writes go to the leader and are sent by the leader to the followers, and it waits for the acknowledge of the majority of followers. Not all followers, so the majority. Typically, replication factor 3, you write to the leader, it sends to the two followers, and when one answers acknowledge, then your write is acknowledged. So that's the way where you have consistency with the best possible performance. It's not like two-phase commits that has to wait on all nodes. It's the fastest you can do. And then you are guaranteed that if the leader crashes or is not available because the network failed in the middle, then the two followers for this tablet will know that the leader is not there anymore because they didn't receive earth bits, and they will talk together to know which one has the latest changes. Because we waited for the majority, we know that one has the latest changes. So if they compare, they know, and then they elect the new leader. So typically how it works, your application just continues for a few seconds. It can hang if writing to this specific tablet because of the TCP IP timeout, but the new leader is already available after 3 seconds. By default, we elect a new leader after 3 seconds because you don't want all this to happen just because there is a few milliseconds glitch in the network, for example.
Yeah, and I love the thing you mentioned, that the idea of ensuring this majority has the latest data is exactly that if leader goes down, the majority already has the latest changes and they can resynchronize. If they don't have, then it's okay, right? They don't have, and that's it. So just to kind of summarize a bit, so we have kind of this data is kind of distributed in two ways, maybe. One is kind of replicated data, and another is kind of splitting these big chunks, table chunks, onto different shards, right? That's That's kind of
Yeah.
two ways we do. And I think you mentioned it, but I still want to kind of I want you to explain it again. So when we have these shards, right, on like single table can be distributed along different nodes. And when we use these indexes in that case, so how does that querying happen? I mean, do we have some single place which tells us which shards to kind of ask with that index, or how does that happen?
Yeah, there is a single place. The idea when you have a distributed system is that everything that is a single place must not be in the critical path.
Yeah.
So there is a single place that we call master. I don't really like this name, but yeah, it's the metadata of the cluster. So the master knows about all the nodes that are in the cluster, where are the tablets. It also holds the Postgres catalog that must be shared by all of them, but it's not in the critical path because all the servers have a cache of this information. So only when you add new nodes and then the master updates the tablet placement and sends it to the other node. But for normal operations, what your application is doing, you do not rely on it. So because if you think about it, if you have a cluster on multiple regions, this master will be only on one region. It has also the same replication with two followers, but when we need information from the master, it goes to one. So we cannot add those 100 or 200 milliseconds in the latency of all SQL queries. So basically, you have this latency, for example, when you connect or when you add a new node, this new node must get information from it and then has to read from the other. But basically, the idea is that you don't need this master. And if this master is down, the normal operation continues. So first, because this master has followers, so it will never be down. But even if they are all down, normal operation can continue. It's just the rebalancing cannot happen and some DDL cannot happen. So it must be resilient also, but it's not as critical as the tablet servers, which where data belongs. And maybe something I can add also about this latency when you are cross-region. I mentioned that the reads had to go to the leader, but there are some cases where you have read-only transactions just for reporting, and you don't really need to have the latest data. You can read a stale snapshot from 15 seconds ago, and then you can read from the followers in that case. If you set the transaction as read-only, because if you write, you cannot read something that is stale and write something, then you will corrupt. So if you do only reads and you accept this few seconds staleness, it reads from the local follower, and then the reads can be quite fast, even when it is distributed across multiple regions.
Yeah, and just one thing like about this indices and things kind of metadata stored about the cluster. Is that thing what Zookeeper is used for, or that's something else?
We don't use Zookeeper, but you can think of it about something similar, but it uses the same, basically it uses the same code as the tablets.
Yeah.
This master is just one tablet.
Yeah.
You don't need more because you have the metadata, the catalog, that's maximum 100 gigabytes. But it's also replicated by Raft, and it's typically quite independent. For example, when we deploy on Kubernetes, we deploy this master as another stateful set. So we have a stateful set for the master and the stateful set for the tablet server. But typically, the tablet servers, you add more. But if you are in replication factor 3, you don't need more than 3 masters, one leader and 2 followers.
Yeah, so basically this is a separate kind of small distributed database on its own, right? Nothing else. Yeah. Amazing. So, and just to kind of wrap this whole thing, which I'm super excited about, is that how these big things are created with small components, and these small components are built independently, like in Yugabyte, like you mentioned, this Postgres layer, this RockDB layer, then there is this Raft and this distributed mechanism which does this synchronization, etc. So that's super exciting. And I mean, Thank you a lot. I mean, it was blast talking to you. I think we just created an amazing database resource for everyone out there. I had like amazing pleasure and blast today. And yeah, so thank you once again. It was my pleasure to talk to you.
Thank you. For me, it's also really interesting, and those technology are amazing, and it's fully open source also. So everything, even the roadmap, the architecture is open source. But of course, there are many components, so it's easier to talk about it.
Yeah, for sure.
Many of those things I've learned that 2 years ago, because when I was working with monolithic databases, this is I didn't know about Raft. I didn't even deploy on Kubernetes. Makes no sense to deploy Oracle on Kubernetes,
Yeah.
for example. So I've learned also those things. Being a developer advocate is also the advantage that you talk about it and then you learn while you are talking also.
By the way, final question. What do developer advocates do? And that's it.
Yeah, basically, I consider developer advocate as a user that is paid to use and give feedback.
Yeah.
So basically, the database is open source, and the big advantage of being open source is to have feedback, Git issues that we can solve. So without it, it would be impossible to build a database in a few years. But the goal of the developer advocate is to help users to start with it, because not everything may be well documented, for example, and also getting feedback. So I really love when people have questions. Of course, I'm happy to help them. A question to deploy, or question to tune their SQL or whatever. But even if they don't have questions and everything works, I also love to have feedback about which kind of use case they use it, and what we can improve, or just maybe there are some use cases also where I didn't think about it.
Yeah.
So always good to have maximum feedback here.
Amazing. Thank you once again.